So we will review solution of such linear differential equations through another example, which is this one. Okay, a second order differential equation. So what we first do is that we set up an auxiliary equation of this form, okay, by just by taking dy dt as s, okay, and this as, here we are taking it as s square, but you know that is not a square. If you refer to our discussion in which we derived this method, so you will see what we mean with that. But anyways, this is the way we set up our auxiliary equation. Here we put s square, then 2 times s, then plus 3, and that equals 0. Now we are going to use the quadratic formula, and I'm not rewriting it for you in this course. So we will have negative b plus minus b square, which is what? 2 square, right? Minus 4 times a is how much here? 1. So 4 times 1 times c is how much here? 3. Okay. And then divided by 2a. So what do we get here is we have s equals 4 minus 12 is negative 8, and then we have, after that, we got negative 8. So this square root can be split as a product of two square roots, right? And you know this part, this is a complex number I, okay, and so we further change it to, we can see, we can write a square root of 8 has to a square root of 2, okay, and then we are going to write I for this value, okay, and then what we have, we can factor a 2 out upstairs, all right, like in here, okay, and when we factor a 2 out, what do we get? Negative 1 plus minus square root of 2 times I. Alright, and then the 2's will cancel, and we simply have negative 1 plus minus square root of 2I. Okay, so once we have two complex roots of this auxiliary equation, of this form, which is of the form, remember the way we discussed when we were developing the method, we have alpha plus minus I beta. If they are the roots, then what we get as a consequence of that is that e to the alpha t, okay, cosine of beta t, all right, and e to the alpha t, and then simply the sine of beta t. They are linearly independent solutions of this system. You can just, for practice, go back and check if you would like once again. So what was we see? So we have an equation in y and t. So what this will do is that we can write the general solution as, take the constant c1 here, okay, and then you have this, then plus c2, okay, and then we got this, right? Okay, good. So this is the general solution. Now we have to do what? We have to incorporate these initial conditions, okay? So first one, like y at 0 is 1, you know, this is yt, strictly speaking. So if we substitute t as 0 in here, then what do we get? we get e to the 0 cosine of how much? 0, and then e to the 0, and then sine of 0, right? And so this would be how much C1 will become. C1 is, this is 1, right? Cosine of 0 is 1, e to the 0 is 1, and sine of 0 is 0. So this whole thing is gone. And here I think I have done a lazy thing. Remember this? I just copied it from there and did not write the values of alpha and beta, which did not hurt us much in this case because our t was 0 for the initial conditions, but it would have created a problem later on. So we got what do we have? I don't know why am I doing it like this. So here simply square root of 2, okay, and then I have negative sign, and this becomes what? Square root of 2 again, right? So our C1 is how much? 1, okay? And then we will do this. Let's differentiate this equation to get our value of C2 because we have to apply the other condition. So if I differentiate this, actually a better, I think a little time saving effort will be this, that let's factor e to the negative 2 out, no, sorry, negative t out, okay? Then what we remain with is this in here. That might save us a little time in using the product rule while doing what? While differentiating this equation, because we have to apply the condition on derivative. So for the product rule, what I'm doing, we are recalling lots of things in one video. So I have product of two factors. So here, when I product of two quantities. So when I differentiate this by chain rule, I get negative e to the negative t. This stays unaffected. And then plus we have what? E to the negative t again, okay? And then I'm going to differentiate this, and we have to use the chain rule, okay? And so when we use the chain rule, what will we get? The derivative of cosine is negative sine. Let me just temporarily make it a little smaller, okay? And then I have what? Square root of 2. Again, I'm using the chain rule because derivative of cosine of a quantity is negative sine of the quantity times the derivative of the quantity, right? And same thing applies here. So we have a square root of 2, and as I said, first thing was the derivative of sine. Oops, sine will be cosine, right? Now we are going to substitute our 0 in here, or let's just talk, let's just converse about it because you can write it out. So we have the derivative of y at 0 equals 1, and if we substitute t equals 0 in here, on this side, this will, cosine of 0 will be 1. So the first thing we get is e to the negative, I don't know why am I writing it, that has become 1 anyways. So the first thing I'll get is negative c1. Okay, so that's what this whole thing becomes. And then when we substitute t equals 0 in here, this part will become 0, and we will get a square root of 2 c2 here, and this is going to become 1, right? And I think we just determined c1 as 1. So what do we get then? We'll put our c1 as 1, and let's go back and enlarge it here. And in fact, it is a negative 1. So what happens now is this quantity will be 2, and then C2 is going to be simply how much? 2 divided by square root of 2, that is square root of 2. So what our answer will be then for the initial value problem? We got this here, right? C1 is 1, okay, and who is my C2? That's square root of 2, okay. So I'm also attaching this script, and if there is any difficulty, just let me know, okay.